Okay, today we're going to talk about section 3.7. And in it we'll talk about inverse functions. Okay. Inverse functions, they undo what a function does. So that's their purpose. Inverse functions will undo that. So let's look at some inverse functions that we've already known. Okay. So for example, well, if we have a function and let's just make it our basic parent function x cubed. Okay, we could solve equations like x cubed is equal to 8. And the way we do that is that if x cubed equals 8, then we would take the cube root of both sides. Then the cube root and the cubing undo each other. And the reason why they undo each other is because they're inverse functions. And will leave us with just x. And then we'll see the cube root of 8 is 2. Okay. So we've used inverse functions quite a lot. Then g of x equal to the cube root of 8, or cube root of x. These two are inverses. So for example, if we had to solve the cube root of x is equal to 3, okay, we could cube both sides. The reason why that would happen is by cubing a cube root, these two would undo each other and we would be left with x is equal to 3 cubed, which is 27. Okay. So these two are inverses of one another. Now, let's just think in general. This is a very powerful diagram, but let's think about that. Let's say we have some group of numbers here, and this represents the domain. Okay. So in it we usually have some elements. Usually we call them x's. Okay. Now, we can put that element through a function. And what comes out, if we took all the various elements, we'd have a whole other group of numbers, and this would be the range. And we usually denote these by some y. But let's say I wanted to start with the range and ask myself, well, how did I get here? That is, what element in the domain got me through f inverse into the range, or through f, to come out with this y. And the way that we can do that is if we put y, we're looking for something that will take this y and get us back to where we originally started, and that is known as f inverse. Okay. This is the notation for f inverse. Now, when we think about it that way, this group of numbers here, if we're thinking about f inverse, this group of numbers here now represent the domain of f inverse. And what comes out then gets us back to our original x, and therefore this is the range of f inverse. So for clarity, we should really say that this group of numbers is the domain of f, and this group of numbers is the range of f. But what that means then is that the range of f and the domain of f inverse, well, they're the same group. So these are equal. And the same here with the domain of f and the range of f inverse, these are also equal. So that's the role of f inverse. Okay, it's to get us back to where we originally started. Now this is the notation for f inverse. Okay, we take the whole thing as f inverse of x. It does not mean, this is not an exponent. So it does not equal 1 over f of x, okay? This is not an exponent, okay, to the first power. It is f inverse how we read it. So keep that in mind. Okay, so let's think about some very simple functions and see what we can find out about functions and their inverses. Okay. Alright, so let's say, for example, our function is a simple linear equation, 2x minus 4. If we made a table of values for this, looking from -1, 0, 1, 2, and 3, let's say, if we put them through here, we would get -2 minus 4 is -6, 0 minus 4, 2 minus 4 is -2, 4 minus 4 is 0, and 6 minus 4 is 2. And this would be f of x. So what's happening here in the function is that it takes x, multiplies by 2, and subtracts 4. So what can we say about f inverse? If we need to undo what's happening to the function, well, let's undo it differently, okay, in the reverse order. Instead of subtracting 4, f inverse needs to add 4, and then, instead of multiplying by 2, we need to divide by 2. So in this way we can logic it out that f inverse of x needs to take x, add 4, and then divide by 2. Just by pure logic. Okay? If this is f, then this is f inverse. Now, let's do a table of values for f inverse. If we are correct, okay, so these were the domains, and this is what it maps to. So in this diagram, here are x's over in here. They've mapped over here to the range. Okay. So if f inverse is to work properly, if we take these y values and put it through the inverse, we should come back with these numbers. Okay. So let's see if that happens. So we will take, let's see, -6, -4, -2, 0, and 2. And let's put them in. Okay. So -6 plus 4 is -2 over 2, which is -1, which is what we have. Good. Here, -4 plus 4 is 0. 0 divided by 2 is still just 0. And we have that. -2 plus 4 is +2 divided by 2 gives us 1. 0 plus 4 is 4 divided by 2 is just 2. So that's good. And now if we put in 2, 2 plus 4 is 6. 6 divided by 2 is 3. Good. So we've determined the correct inverse for this function. So what we can see here then is that we have a flipping of the coordinate pairs. So on this graph, we'll have -1, -6, but on our inverse graph, we'll have -6, -1. Here, we'll have 0, -4, and here we have -4, 0, and it continues. 1, negative 2, negative 2, 1, 2, comma 0, 0, comma 2, 3, comma 2, 2, comma 3. Alright, so let's see if we can set this out graphically. Okay, so we need negative 6's in each direction. 1, 2, 3, 4, 5, 6. Let's see, negative 1, 2, this is negative 3, this is negative 4. Okay. Then we'll go positive 6. Okay. Alright, so let's graph. First, for a guide, I want to put in our 45-degree line. So when x is 1, okay. Let's see if I can get this. Okay, I'm going to try and be very neat about this so we can see it happen. I'm drawing in the line y equals x. Okay, we'll see why I'm doing that in a minute. Okay, now let's try and draw these other lines. Okay, so 2x minus 4. We're at negative 1, negative 6. Okay. At 0, we have negative 4. 1, 2, 3, 4. 1, comma, negative 2. At 2, comma 0, and at 3, we'll have 2. Let's put another one in. 4, 8 minus 4. 8 minus 4 is 4. 1, 2, 3, 4. Okay. 8, comma 4. Oh, is that so good? Not 8, comma 4. Good grief. 1, 2, 4, 4, comma 4, comma 4. Okay. Sorry. All right. Well, let's see if I can connect these. I don't think I did such a good job. I didn't do such a good job today. Okay, well, it's alright. We've got everything labeled. We're going to make it true, and then I'm going to show you a different way. Okay. Alright, now let's do the opposite of it. Okay, negative 6, negative 1. And then negative 4, 0. Negative 2, comma 1. 0, comma 2. And then 2, comma 3. Okay, now let's see if I can connect these. Get a better looking line. Come on. Okay, well. That's not so bad. Okay. I'm trying to show you a relationship that happens with the line y equals x. Because what we're looking at is that we're looking at the pairs that have just been flip-flopped in the inverse. Okay. So let's go to Desmos so you can see just a little bit better what I'm about to say. Okay, so if we start graphing, okay, so our first function is 2x minus 4. Okay. So that's this line that we've put in. Now we said the inverse was that we added 4 and then divided everything by 2. Okay, so there's our inverse function. Okay. Now the relationship I'm trying to show you is, let's put in the line y equals x. Okay. Now when you do that, okay, here's f inverse, and this is the line y equals x. And because it's a flip-flopping of points, I hope you can see that there's a new symmetry here, that the line f and f inverse are actually symmetric with respect to the line y equals x. Let's try another one and see if that still happens. Okay. We said at the beginning that x cubed there's x cubed, our parent function. Let's zoom in a little bit more so we can see it just a little bit better. Okay. And then we said the cube root of x was also the same. Okay. Now remember, I can write the cube root of x as x to the 1/3 power. Okay. Right. So notice this, and perhaps it's even more clear here. When you're looking at these, we have a very clear symmetry. And if I put in the line y equals x, it goes directly through this. Okay, so that is to demonstrate the symmetry. Okay, so we should make a note here. A function and its inverse are symmetric with respect to the line y is equal to x. Okay. So let's try another one. Let's see if we had to do this graphically. Okay. Let's say, for example, we were just given a function. And it looked like so. And this is the point 0, 4. Okay. I don't know what function this is. It does have the shape of x cubed, and it's been translated up 4 units. So let's say that's what it is. F of x is equal to x cubed plus 4. Now, I don't know what the inverse is going to look like, okay? But I do know a couple things. I know that the inverse needs to be symmetric with respect to the line y equals x. So let's draw in that 45-degree line and see if we can't do a sketch of what it should look like. And the only other thing I know is that if 0, 4 is on the function, then, let's see, approximately, then 4, 0 needs to be on the inverse, okay, by the flip-flopping of points. Now this function is coming down and getting closer and closer and closer to the line y equals x, so if I'm to draw the symmetry, it should look like so. And then if this is getting further and further away, f inverse should also be getting further and further away to maintain the symmetry. And so this is f inverse of x. Okay. And so that's how I could just sketch the graph of that. Now let's say I actually wanted to know what f inverse is explicitly, given that I have this function. Okay. Well, to find the equation of f inverse, okay, it all comes down to what we know, that there's this flip-flopping of points. Okay. So let's write f of x as y, and then is equal to x cubed plus 4. So f of x does play the role of y. Okay. Now, because it comes down to this flip-flopping of points, let's switch x and y. So in that case, I mean that we should have x is equal to y cubed plus 4. Okay, so that's what I mean by switching x and y. Okay. And now we can solve. And we'll be solving for y. Okay. Alright. Well, let's get y cubed by itself, so we'll subtract 4 from both sides. So x minus 4 is equal to y cubed. And then we can just take the cube root, using the fact that these are inverses, to get to y is equal to the cube root of x minus 4. So in this way, we've found the equation of f inverse. Alright, now finding the equation is different from verifying the equation. Okay? What we know is this. What we know is this. If you take f and into it you put f inverse of x, because these are inverses, what you should get out is what you put in, which is x. Okay? Of course, there's a little caveat. It's for all x in the domain of f inverse, because that's what's going in here. We might have some domain problems coming up. Okay? Alternatively, if you take f inverse and into it you put f, since they are inverses and they undo each other, you should also get x back. Okay, so this is the input. And of course then we still have the domain worries. That's for all x in the domain of f. Okay. All right. So we say that these two are inverses, okay, that x cubed plus 4 is inverses of the cube root of x minus 4. Okay. Let's verify that. So let's call this let's call it g of x, just because it's another function. Okay. So to verify that they're inverses, I need to take one function and put it into the other. So let's start with f, and into f I'm going to put g. Okay, so what does that mean? G, we decided, was the cube root of x minus 4. And that needs to go into our function f. Okay, so f takes something, cubes it, and then adds 4. And the something that we're looking at is the cube root of x minus 4. Now we need to simplify this. Okay. If they're going to be inverses, we'll have to get x back out. So let's see. Now the cube root and the cubing will undo each other, so we'll just be left with the x minus 4 plus 4. And then minus 4 plus 4 is just 0. So we do get x. That's a good thing. We've met half the criteria. Okay. Now we have to show that if we take g and put it into f, that we also get x. Okay, so let's see how that works. Into g, we're going to put f, and f is x cubed plus 4. Okay. Now g takes the cube root of x and then subtracts off 4. Okay. And instead of x, we're putting in x cubed plus 4. Okay. Now let's simplify. Okay. So this is the cube root of x cubed plus 4 minus 4, which is equal to the cube root. Now x plus 4 minus 4 is just 0. So we get the cube root of x cubed, which is just x. And therefore, by using function composition, we've shown that f of x and g of x are in fact inverses. So those are two different things. When you're asked to verify, you need to use function composition. And if you're asked to just find the equation, then you can do it this way. Okay. Now, let's revisit this topic of one-to-oneness. Okay. Now, let's say, for example, let's say this is the function y is equal to x squared. Okay. And we can put in, now if we're going to flip-flop the points, this graph needs to be symmetric with the line y equals x. And what will happen is that the parabola will then lay on its side. So this is y, which is equal to a function. Okay. Now, what I've drawn here is f inverse of x. The question is then, is f inverse a function? And clearly, f inverse is not a function because if I draw the vertical line through it, it passes more than twice. Or more than once, I'm sorry. It passes through twice, more than once. So this is not a function. Which is curious because in this example, I had a function, and when I flip-flopped its points, f inverse was still a function. So the question becomes, how is it that some functions have inverses that are functions, and other functions have inverses that are not functions? And the answer to that is that one-to-one functions have functions that are inverses. All right, so let's. So that's a keynote to note about why some are and why some are not. All right, let's find the inverse of a rational function. Okay. So let's say, for example, that we have f of x, which is equal to 4x minus 1 over x plus 2. This is a rational function. And let's find the inverse, find the equation. So to do that, we have to change f of x to y. Okay. And then let's switch x and y. Okay, so this will become x is equal to 4y minus 1 over y plus 2. Before we move any further, let's make sure we know about this. We know then that the domain for this rational function is the set of all x such that x cannot equal 2. Okay? We just have to exclude 2. Okay. Now let's solve for y. Well, the trouble is that I have two y's, and one of those y's is in the denominator. Okay, so first of all, let's get rid of that. And the way we could do that is, let's multiply through by this denominator. So on this side, they will cancel, and on this side I'll have y plus 2. So over here, we just have 4y minus 1. And then let's distribute this x through. So xy plus 2x. Now we still have the problem that we have two different y's, but at least they're not in the denominator anymore. Okay. So if we're going to try and solve for y, let's at least get the y's on one side, the terms with y. So let's move this one over here. And then this one doesn't have a y, so let's move it over. Okay. So to do that, I'm going to subtract 4y from both sides and subtract 2x from both sides. So we'll get xy, and then I'm subtracting, I'm subtracting 4y from both sides, and then I've subtracted 2x from both sides. Okay. Now the help with doing that is that, again, we still have two y's, but at least they're on the same side. If we're going to solve for y, we only need a single y. So at this point in time, there's nothing I can do to simplify on this side. And the only thing I can do on this side to simplify is to see that there is a common factor of a y in both of these, and then factor it out. And now we're done. We've turned two y's into a single y, and I just want to solve for y so I can undo what's happening to it. So if I'm multiplying by x minus 4, I could divide by x minus 4. Then those will cancel, and I would be left with y is equal to negative 2x minus 1 over x minus 4. And since we went through so much trouble determining this, let's at least label it as an inverse. Okay, so we know this. And let's see if the domain of this. Okay, so the domain of f inverse, well, that's the set of all x such that x cannot equal 4. Now a harder question becomes, what is it about the range of f inverse? What if I wanted to look at that? Alternatively, what if I wanted to look at the range up here of f? Now this is not so clear, just looking at these functions, either one of them, what the range is. Okay. But if we go back to our diagram from the beginning, and this is one of the reasons why it's a very powerful diagram, I see that the domain of f has to be the range of f inverse. So if I'm asked about the range of f inverse here, well, I know that has to be equal to the domain up here. So I could just write this in now, not as x's anymore, but as y's or something. It has to be the range of f inverse is the set of all y such that y cannot equal to. And from here, the domain of f inverse was x can't equal 4, but the domain of f inverse has to be the range of the function. So we can come back up here and say, again, the range, we'll call it a y and not an x anymore. It's a set of all y such that y cannot equal 4. So that's a very powerful tool for us. Okay. Now this is how we found the equation, and we hope we've done well. Now let's actually verify that f and f inverse are functions, okay, or are inverses of one another. So let's verify. Okay. First we need to take f, and into it we're going to put f inverse of x. So that means into f we're going to put this rational function here. What did we say f inverse was? F inverse was negative 2x minus 1 over x minus 4. And now we have to put that into f. Now f says we're going to take 4 times this, subtract 1, divide by this, and add 2. Right, so let's fill that in. Alright. Okay, this is going to take a little bit of work, but we can do it. Okay. Now, we have a fraction, and we need to add something to it, so let's remember we can write these things. Now, working in the denominator, if I want to have the same common denominator, I have to multiply this by x minus 4 and this by x minus 4. Okay. So let's just work with the denominator first. Okay. So I'll just copy this, negative 2x minus 1 over, and I'll write it over our common denominator, x minus 4. Okay. Then I'm going to add to it the 2, and remember that that has to be multiplied by the x minus 4. Now, x minus 4 is going to be the common denominator for up top as well. So up top, I also have common denominator of x minus 4. In this first term, I have to take 4 times negative 2x minus 1, and then I'm going to subtract this x minus 4. Okay, let's simplify this. So to do that, we'll distribute this 4 through. So we'll get negative 8x minus 4, and then distributing this negative through, don't forget your parentheses, minus x plus 4. All of that stays over x minus 4. And then we're dividing that through by negative 2x minus 1 plus, and then let's also distribute this 2 through. 2x minus 8. And all that stays over x minus 4. Okay, so this is being divided by this. Okay, so let's simplify up top here. So negative 8x minus another x is minus 9x, and negative 4 plus 4 go to 0. That's good. Okay. and all that's divided by x minus 4. Now I'm dividing two fractions, so I'm going to flip this, x minus 4 over. And then let's simplify in here. Negative 2x plus 2x goes away, and negative 1 goes to 0. Negative 1 minus 8 is minus 9. Changing the division into the multiplication. Okay. And now we can see all this canceling occur. Okay. These x minus 4s and this x minus 4 is going to cancel. This negative 9 is going to cancel with this negative 9. And we're just left with x. And that's what we wanted. Okay. So when we put f inverse into f, we received x. And that's what we wanted. But we're not done. We have to do it the other way as well. We have to take f inverse of x and put f into it. So that means we're taking f inverse of, what did we say? F is 4x minus 1 over x plus 2. Okay. Now, f inverse is a little more difficult, but we can do this. This is negative 2 times x, where x will be this. Then we're going to subtract off 1 and divide through by x minus 4. So this is 4x minus 1 over x plus 2. This is 4x minus 1 over x plus 2. So this is going to work exactly the same way. We need to get common denominators. And that common denominator will be x plus 2. Okay, so let's see what we'll have up top then. So in the bottom, x plus 2 will be the denominator for both. Then this first term has the negative 2 times the 4x minus 1. And our second term is the negative 1 times this, which is the same thing. You could write in the negative 1 if you want. That's fine. Now down below, this 4x minus 1 just stays the same, because it's already over x plus 2. But here, we have this negative 4 times the quantity x plus 2. Okay. Now let's do some distributing. Now up top here we have negative 2 times positive 4 is negative 8x plus 2. And from here we have to distribute the negative 1 to get minus x minus 2. Then down below, well, the 4x minus 1 just stays. But I'll have to distribute this minus 4 through. So minus 4x minus 8. Okay, again we're going to do some dividing. Okay. So simplifying this first one, minus 8x minus another x is minus 9x, and the plus 2 minus 2 is 0. That's over x plus 2. Now I'm going to flip and do the multiplication here as well. So the x plus 2 comes up top, and then down below, 4x's minus 4x's goes to 0. So we just have minus 1 minus 8, which is minus 9. And now we can do the canceling. So this x plus 2 will cancel with this x plus 2. This negative 9 will cancel with this negative 9. And we are left with just x. Therefore, Okay, that's that little symbol there for by using function composition. We have shown F and F inverse are inverses. So you'll be asked to demonstrate this on your exams and on your homework and on the worksheets. Alright, let us do one more example. So let's say we're given this graph. Okay. Now, this is a function g of x. So let's say that we're supposed to find g of 3, okay, and then g inverse of 3. Well, if this is g of 3 is equal to 1. So that would mean g inverse of 1 must equal 3. Now what if we asked, what about g inverse of 3? Well, that's a little different question because we're not given g inverse here. What we're given is g. Okay. But remember, in g inverse we would flip-flop the points. So on g inverse we would have the point 3, 5. So if we were looking for g inverse of 3, what would have to come out is 5. Okay. So when you're given the graph of a function and asked about the value of the inverse, remember to flip-flop those points. Okay. So here's our solution. Let's see. To evaluate g of 3, we find 3 on the x-axis and find the corresponding output value, which is 1. So that tells us g of 3 is 1. Now, on the other hand, if you're evaluating g inverse of 3, recall the definition means that the values of x for which g of x equals 3. So when we look for the output value of 3, which is here, we find the point 5, 3, which means g of 5 is equal to 3. So by flip-flopping the points, g inverse of 3 must be equal 5. Okay. Alright, so that's going to take a little bit of practice. I think it should get you through your homework. Email me if you have any questions.